can you unmute and share your screen?
Yeah, sure.
Okay, yes, it's working, good. Great. Good, and since I'm somewhat embarrassed since this is a virtual session, I didn't get a chance to ask you how to pronounce your name.
Yeah, Rafiqul Rabi.
Okay, great. So the final talk of the session is going to be by Rafiqul, and he's going to talk about syntax-guided program reduction for understanding neural code intelligence models.
Thank you. Hello everyone, I am Rafiqul Islam Rabin from University of Houston. I will present our paper on syntax-guided program reduction for understanding neural code intelligence models. Deep learning has increasingly been used for various code intelligence tasks. In those tasks, the model takes a program as input and makes some prediction about the underlying downstream task. For example, predicting method theft or detecting bugs. Although successful in modeling source code, the problem of explaining why models make their prediction is still challenging. This is because the deep neural models are opaque black box for little insight into the features they use in making their predictions. In this regard, we propose a model-agnostic approach to identify relevant input features to a model's prediction. This is an example from the method prediction dataset. A developer looking at this program could provide several explanations why this is on-get method. For example, there is a super.onGet invocation that strongly suggests this method overrides a method with the same name in the parent class. Also, if developer familiar with Android activity, they can recognize that onGet method is used to initialize a user interface with set continuity. A trained code intelligence model, for example, code to break or code to can correctly predict this code snippet as onGet. But it is difficult to understand what feature actually such models use for making this prediction. To improve the transparency of models prediction, we aim to extract input feature that models have learned during training. This is the high-level overview of our proposed approach for extracting key features from input programs. In our approach, we adopt program reduction algorithm to remove irrelevant parts from input programs and create candidate-reduced program. The approach then checks prediction of the target code intelligence model on the candidate-reduced program and continues reduced program by preserving the model's prediction. Finally, we extract the key features from the reduced programs. In our previous work, we used data debugging as a reduction algorithm to reduce the size of an input program. Given an input program P and a model M, the approach first records the target prediction Y given by the model M on program P. The data debugging then produces a candidate program by removing some part from the original input program. If the reduced program does not provide the same prediction Y, it then rejects this candidate and next it creates another candidate by removing some other tokens from program. It then iteratively churns to this program that produces the same prediction as the original input program. However, the data debugging approach does not follow the grammar of programming language during the reduction and create a large number of invalid programs, which hinders the overall performance of the reduction. Therefore, in this work, we adopt PERSYS as a reduction algorithm that follows the grammar of programming language and always generate valid input programs. Given an input program P and method M, the approach also records the target prediction Y given by the model M on program P. PERSYS then parses the input program into a parse tree by normalizing the definition of grammar. Then it traverses the tree node by node and determines whether a tree node is deletable, depending on whether it preserves the same prediction after deleting that node. It repeatedly checks the tree node and prunes the subtree when the node is deletable. And the remaining is the final reduced program where no further node can be deleted and still produces the same prediction as the original input program. We have applied our approach for the method and prediction task approach to popular code intelligence model, code to bake and code to set on the Java large data set, considering different type of input programs. We first discuss our approach for automated feature extraction and then demonstrate how it can be used for adversarial attack, and then provide a comparative analysis between data debugging and parsers in terms of their performance in reduction. In our previous encrypted embedding on, we attempt to find key features of a level by manually inspecting some input programs of that level and then train a SVM model. However, this manual inspection does not scale to large dataset with many levels. To automate the feature engineering for extracting key features from input programs, we apply our prediction feature reduction approach. Evaluate a model and a set of sample programs of a target level, we apply the program reduction approach to reduce those input programs, and after reducing a set of input programs of a target level, we extract tokens from the reduced program, and the most common tokens are identified as key features. For example, these are the key features for these levels came up with our automated feature extraction. So there may overlap between the model's extracted feature and the download encrypted feature marked as the blue color. So extracting those features can help developer to verify whether a model is learning a specific level correctly or can help debugging the cost of in case of misprediction. And by extracting the key feature for all levels, we are actually representing an abstract from model's feature space, and the learned feature space will become more transparent. In our another previous work, observed that models are very sensitive to variable lengths and often change their prediction on variable renaming transformation. For example, in this original program, there are 4 variables. If we rename any of these variable names, the model may predict the program. But which variable is more sensitive to adversarial attack? We can find such potential vulnerable variable by looking at the program. The variables that are kept in reduced program are more likely to sway the prediction of original program. While in our previous work we create candidate adversarial example considering all variables of original programs, in this work we create candidate adversarial programs on key variables from reduced program. And we observe that in each scenario the number of generated candidate examples based on key variable is almost 50% lesser than the number of candidate examples generated considering all variables. But still it can trigger more than 10% misprediction. Also comparing between DD and parsers, we can observe that the parser generated candidate programs are more vulnerable to adversarial attack with general candidate compared to the data debugging. So this might be highlighting that the importance of key tokens found in parser generated previous program are more level specific than the data debugging generated key tokens. Finally, we check a comparison between the data debugging and parsers on the reduction performance. And we compare the performance in terms of the total number of token reduction, the number of steps it takes to reduce the input program, and total times it spent. And we check for different kind of input program, like frequent input, the example that appears more frequent, or the rare examples, the example with a smaller statement, or the example have a larger statement. And from our experiment with different input types, we observed that parsers always allow more token removal than data debugging, and it takes a smaller reduction step, and that's why it spends less time than data debugging to reduce find the final reduced program. Using different reduction technique, we can find different potential explanation about a prediction. For example, a code intelligence model predicts the code snippet as the on-kept method. Using data debugging with tokenless program reduction, we can see that set content view has an important role in the target prediction. On the other hand, when we apply tree-based parsers, it highlights the presence of same override method in the program. Having this multiple explanation for a specific prediction may provide additional explanation for the transparency regarding the model's prediction. However, the challenge is how can we summarize the different rules from the defined approach? In future, we plan to focus in this direction. In summary, we adopt persist as reduction algorithm for extracting key features that models have learned during training. Using the syntax information, persist improves the performance of the reduction, as the reduction only explores the space of syntactically valid programs. The adversarial evaluation with key identifier also highlight the importance of key tokens found in the reduced program. And finally, by analyzing reduced program for key feature based on different reduction algorithm, we may better understand the reasoning behind the model's prediction. Thank you. We have made our artifact publicly available for further study.
Thank you. Okay, do we have any questions? Yeah, go ahead.
Thanks for the talk. I have a question. Maybe you explained this, but I don't understand. Generally, program reduction algorithms require.
Thank you. Any question?
Yeah, can you hear us?
Yeah.
Okay.
Okay. Can you hear me now?
Oh.
Yes.
Oh, okay, fair enough.
Can you hear me?
Yeah, it could be practical.
Can you hear me?
Not clear.
Can I type your question in Slack?
Oh, yeah, right, or maybe, you could go to my laptop.
Maybe you can.
Yeah, or you can
from
put the
Yeah.
laptop. You can hear this, right?
Yeah, yeah.
Okay,
yeah.
why don't you just speak to the laptop?
Thanks for the talk. You mentioned that you used program reduction techniques here, but generally these reduction algorithms require some sort of specification or some unit tests. Who provided those tests? What is the
Okay,
reduction
so-
target?
Yeah, reduction target is like so we have a model and a model given a like input program the model to make the prediction. So here our target is preserve that prediction. So we will reduce the program input program, but we will preserve the model prediction. Like if the program has 10 lines, then maybe data debugging randomly remove 2 or 3 lines, and then the remaining statements we will consider that as reduced input program, and then we will make a prediction based on the model and check whether model is still making the same prediction. So if if model is still making the same prediction, that means the true model uses for making the prediction is present in this reduced version. So then by reducing the program, so our target is find the reduced program, where we can find the key tokens or the clue that actually the model used for making that specific prediction.
Thank you.
Okay. Yeah, thanks. Great, so the next thing on our schedule is the poster session, which was supposed to go from now until the end of the coffee break. The only thing we are missing is poster awards for this. We have been promised them, but so what I would suggest in the meantime is maybe if you have a poster, just kind of spread out somewhere. Boards may or may not appear. You can talk to people, and in 7 minutes there will be coffee outside. Go get coffee, come back. Hopefully by the end of the day we'll have boards, but we'll see.
Yes, I was wondering. I would say.